Hello and welcome back. So we left in the last episode we left till the parametric sweep where actually we provided the optometric values, right, for the swiping parameters, and that's optometrics. We call it optometrics. As you can see, we reached till optometrics part where we defined, I guess, for 35, 45, 55 and 65 the four values were there. So yeah, we did this, and now today we are progressing from here. Okay, so yeah, what we are doing actually, it's wireless power transfer technology, right? So we are trying to transfer the power wirelessly between coils at a certain distance, and the parametric sweep that we are creating is for that distance, the distance between the TX and RX. So first it will calculate all the parameters at a distance of 35 mm, and then at 45 mm, 65 mm, yeah, and that's it, right? The next step, we will actually do the analysis. That means we'll run the analysis, and the analysis will take some time, right, depending on the size of the coil and the complexity of the design we are creating. So because it takes time, we actually designed it on the first place in a very simple way with few number of turns with a very thick wire. It takes less time with the thick wire, yeah, and all the things were considered. So I guess it won't take that much of time because it's a very simple coil, right? So let's see if it ends positively. Okay, so what we do, where we go now, so that we are in draw menu right now, and there is model and there is simulation. So we go to simulation part. Before we produce results here, before we do anything at all, we are first interested in checking if the simulation will work or not. So there is a validate, a green tick mark, big tick mark is there. So just click there and see if everything gets validated, right? So the design settings are good, 3D model, everything is done, mesh operations, analysis setup and optometrics, everything is looking fine, right? At least for Ansys. And now we will click on analyze all. You can also do that thing by clicking on analysis, right clicking and analyze all. So it's the same thing, right? Before we do that, let's check the mesh settings one more. Right click and see the initial mesh setting, because a lot of people actually get error from this corner. Initial mesh settings, sometimes it gets messed up, right? Sometimes it changes to automatic or something like that. I guess TAU is one type and one is classic. We're not going in detail what exactly these two types, what are these two types and how it works, right? So let's just make sure that it's on auto mode, and the slider here is on all the way to the left, right? So use slider setting is on, and in the coarse mesh is on, turned on. So that is what we want. So just make sure that before you run, it's in these settings. Normally the default setting is these only. Okay, so I guess everyone will have no problem in this. So let's just go ahead and click analyze all. Now yeah, it will take some time to run, obviously. Let's wait. Let's see how much more time it takes. We are having a look at the clock. I forgot when I started, but we can later on determine anyway. I'll give you the total time taken during the setup in my type of configuration. The RAM that I have is this 4 GB of RAM, right? 4 gigs of RAM is a very low end device, I would say. And CPU processor, it's i3. Yeah, I'm very old fashioned. So but it's still working fine in my laptop. That means if my PC can do it, your PC can obviously do it, right? So yeah, let's see how much time it takes in my computer. Then I will just give you a reference so that you won't panic when you do the same analysis on your side. I'll give you the total time taken and the configuration that I have. So depending on that, you can just verify how much time it is taking, right? Till the process goes on and the progress is being made, let's just discuss on few points so that we won't lose time. Especially I won't lose that time, right? So we're not going to waste time, and we'll just go and create result. This goes on, so it will take some time, and let's just see the result part. So once the analysis is done and it's complete, we can see the results. So let's just see and build the results. When you right click, you see a bunch of steps, right? And on the very top of the portion, you will see there is a create magnetic static report. That's the solution type we are using actually. And there is also a field report. We'll see what these things are. First, let's go to magnetic static report. This is our solution type report. And there are a few things like rectangular plot, one is a stacked plot, and there is a data table that we might be very much needing. So just go ahead and just see the data table first. So doesn't matter which menu you go inside, it will always bring you to the same kind of pop-up, right? The dialog that will open is almost same, is actually the same one. So when you go there, you can see a few things here. The parameter is we can choose matrix one or no parameter at all. It doesn't matter that much. Sometimes it makes a difference when you are calculating losses, but not right now. And then there is another important factor there, the primary sweep. So the primary sweep is being done in every one of the result that you are seeing is by default, and you can't change that, is the dist, because that's the only variable we are using in the parametric sweep. So dist is, again, to make you remember, it's a distance between the TX and RX, the transmitting coil and the receiving coil that we are interested in. So the same parametric analysis is being done right now, right? So let's just prepare the results, the format first, and then when the analysis is done, we'll just see the graphs. Okay, so what we are interested in, we are interested in few things like coupling coefficient. Okay, coupling coefficient, and before that we are actually interested in the inductance value, right? The L values, and you can see it's Rx comma Rx, Tx comma Rx, Rx comma Tx, and Tx comma Tx. So self to self is self inductance, self to another one is mutual inductance. So we are interested in self inductance as well as mutual inductance. So let's just select all of these and just cross check if the self inductances are equal or not, right? Because we are using the identical coils, they must be equal. And then again, mutual inductance from one coil to another coil should be same to the second coil to first coil, right? So first to second and second to first must be same. So let's just select all of these terms, and just remember to select none here in the function and not maybe magnitude or something like that, because we are not interested in any cross functioning of that, right? So straight the matrix we are interested in, right? Create a new report, and that will create a report for us with all those matrices, and it will create a data table value, right, for different distances actually. Okay, I guess the test is the parametric analysis is completed right now. Yeah, so all the values are listed here, 35, 45, 55 and 65, and for every one of them the self-inductance value is given here. It's microhenry range, it's 1 microhenry. Okay, that's fine. Yeah, and then same thing is with the TX coil and with the RX coil, and obviously they must be equal. So yeah, they are equal. So somehow there is a difference, you can see there is a difference with the distance, though it's not dependent on distance, it happens sometimes because there are a lot of factors that are changing, like the in the finite element method, which is Ansys that uses that, right? And it keeps on changing. It's not constant in every analysis, parametric analysis, when every parametric analysis is running. Like when it runs for 35, it takes like different lengths while making the mesh, right? And again in the 45, the sizes may change and the value may slightly differ again and again and again, right? When it runs again and again, the same thing is not repeated in exactly the exact same way. It is always different, right? Because it's always arbitrary and it converges differently on different times. Because of that, you will see that there is a difference with the distance, though it's not dependent on distance. So it doesn't matter. Somewhere around that, so we can understand this the minimum fluctuation in the values, right? So ignore that. We are more interested in the mutual inductance, and if you see the mutual inductance between the coils, see the mutual inductance is in the decreasing order as we go further, or when we increase the gap, the mutual inductance decreases, and that's very basic and very natural to it, right? So it's in nanohenry range. So when we are at a distance of 35 mm, the mutual inductance between the coil, right, is 217 nanohenry, and then it keeps on decreasing further with the distance. So because of that, the coupling coefficient will obviously decrease, and we are yet to see how exactly it looks like. Right? What's the value of the coupling coefficient when the distance is 35, and what's the value, how it decreases, how slopey it is, the curve, right? So at 65, what's the value? So we are all interested in all these things. So let's go ahead, right? So this was inductance matrix that we created from result. Let's go and create more reports. Let's go and create a rectangular report first. You can select the matrix one or just leave it. It doesn't make that much difference, by the way. We're interested in coupling coefficient. Let's see coupling coefficient. So one axis, that's x-axis, will be the distance, and the y-axis will be the coupling coefficient value, right? So coupling coefficient is always between two coils, so we are interested in Tx Rx, so we'll select this and we'll create a report, and the report is generated. As we can see, for 35 mm it's around 0.2, more than 0.2, 0.21 maybe, yeah, and the coupling coefficient is very less in WPT, and this is a very typical value, as you can see. And in 65, when the distance is 65 mm, it's almost negligible, right? 0.06 is the minimum value, and slightly more than that, somewhere 0.07, I guess. And if you want to see the exact value, how you can actually right click and use the marker mode, add marker. Let's say we are interested at 50 mm distance, then go ahead and just click here. So it's almost 50 mm, right? So you can do it more precisely by zooming in. There is a zoom option right here, or just this will also work fine. So this is how you use marker to get the value. So y-axis value, that's coupling coefficient at 50 mm distance, is 0.1159. Okay, that's fine. And just press escape key to remove the marker mode. That's it, right? So yeah, this is how it changes in between the coils. So let's see what we can do else. Let's go back to the WPT coils and generate the top view. Just hide the region and fit the coil here, and let's use a rectangle. Our solution exists. Do you want to create a non-model object? And yes, we want to create a non-model object. It's not a part of model. It's particularly for different purpose. So we'll press S, and we'll draw a slightly bigger rectangle and then create it like this. And let's see the front view now, and as you can see, it's in the 0th position. Let's move that from the z-axis here, or just create a plate variable, use length, and let's see at 35 mm, sorry, 30 mm. Okay, Yeah, that's fine, looks fine to me, right? So let's go to isometric view, and why we're creating this is to see what's happening exactly with the fields, right? So, and select this object, right click and go to fields, and we'll see the field, right? So we are interested in the you can see vector, you can see the magnitude of the magnetic field there, right? The strength, or you can see the magnetic field intensity also. So anything we are interested in B right now. So how much Tesla is there, magnitude, select for all objects, and just let's see how it looks. So the maximum value is 0.003 Tesla, right? But we can see there is very few less. I guess the red zone is almost negligible, and it's in this part of the plate. Let's change the direction first. Okay, let's change the direction, sorry, the distance. Let's change the distance between the coils to 55. Okay, oh yeah, and let's change the plate distance to 45. Let's see how it changes. Yeah, there's a drastic difference now. The field has increased tremendously in the middle, as you can see, right? So if you want to see the vector, how the vector looks like, field vector looks like, you can actually change it from fields overlay, right? You can add it from here, field B, sorry, the vector, sorry, we need to choose, then assign field vector for all object, and yeah, that's the vector. This is magnetic field intensity, sorry, the magnitude, and this is the vector form, right? Yeah, now it's more clear, and we can see where our coil lies and what part of the coil is being energized. Means it is linking to the magnetic field, the flux, right? Flux intensity, we can see, and with the change in distance it changes actually, and that's all what we're interested in, right? So how the change affects, right? So yeah, this is how we see the different coil design and know to optimize the coil parameters and the size of the coil and the type of the coil and so on and so forth, right? So this is all, right? So we did it, we saw how the field changes, how the flux is linked, how we change the distance, and then how it is affected. Everything is affected between the two coils, right? So if you do not have an idea of what's going around and what part of a system we were simulating, to just clarify that thing, let's just see a very simplified circuit here, a very simplified block diagram, we may say, or a circuit diagram, right? So this is the transmitting side that actually resonates, and then there is a secondary side, receiving side, that also actually resonates, but it's not necessary that it will resonate with the same frequency, with the supply frequency. It might resonate in different frequency as well, right? So yeah, we are not going in again in detail about different topologies or all about that, but the basic fundamental thing is that we have a circuit that runs the transmitting coil and the receiving coil, right? We have a load, we have a supply system. So this is a basic fundamental supply system. We will provide let's say 1 megahertz AC supply, sinusoidal supply, right? And then it will go to the primary resonator, and then there will be secondary resonator, receiving resonator, and then we'll apply load to that side, and we'll see how the power is being transferred, the efficiency of the power transferred. So what's the power transfer capability of the system, how much power it is transferring, and with what efficiency it is transferring, right? So there are a few things we can look into. So yeah, obviously we would want an efficient system. So what we can do to tune the system, first we have to make resonators, right? So till now we have just developed coils, right? It's just inductance, it's an inductor, right? It is still not a resonator, so it won't work in a WPT system. Obviously it's just a inductor. So we can self resonate it, or we can use external capacitors to resonate at a certain frequency, right? So we'll look into that thing by building circuit, and we'll see the efficiency and the power transfer capability of the system by using the same coil that we designed in Ansys itself. But for the circuit analysis part, we'll use another system that is very famously known as Simplorer, Ansys Simplorer, or nowadays it is also known as Twin Builder. So right now there is a Twin Builder system that you can see here. So I have already created that thing. Let's just have a sneak peek, right? So what I'm talking about is, and what we are going to do in the next episode, in the next tutorial, will look like this. And while I say this, my laptop is behaving weirdly. Okay, there it is, right? So a simple sinusoidal voltage source at a certain frequency. These are a bunch of measurement stuffs. There is a normal capacitor, and this is the matrix that we created, right? So we have done the parametric swipe. So this is where it all comes. We just import that thing and bring that thing here in the Simplorer, and then further do the circuit analysis, right? And then there is a secondary side capacitor that is resonating. This is a series topology. We can have series parallel topologies, parallel series topologies, parallel topologies as well. So it all depends on your necessity and the way you are trying to design the system, right? And for what purpose it is. A series topology works quite fine actually, and I'm working in a series topology, so I know a few things about it. So I'll just say those things to you. Maybe it can help in your project as well, or in a similar project that looks like this, or you can get inspiration from this, or you can learn few things from this, right? So we'll go forward in the next about this thing and how we do a lot of other stuff, a bunch of stuff we'll do together. So till then, have a good day, a good night, a wonderful time. Keep learning and keep hustling. Goodbye and thank you. And yeah, do not forget to bring on any queries you have related to any project or whatever you are involved in. Just try to become more detail oriented, or you can even send me the structure that you have prepared in Ansys. So at least it will help me to support you faster, right? Help you faster, or even I can learn few things from whatever you have created, and then maybe we can together come with some solution, right? So that's the whole point of making a community. Let's hope that we are contributing together to our community. Thank you again, and goodbye. Bye bye.